Hi everyone. In today's class, we can see a topic named as linear delay model. So in the previous class, we have seen two different delay model for estimating the delay in a combinational circuit. One is an RC delay model that which employs a single R and C element for computing the delay, and the second method what we have seen in the previous classes is an Elmo delay model. The key advantage why we are going for this Elmo delay model is you can use a series of a resistance and a capacitance for estimating the delay in the combinational circuit. Now the third model what we are going to see now is linear delay model. In the case of the linear delay model, the delay, that is the normalized delay, is represented as D, and the formula for computing this delay will be equal to sum of two different terms. One is expressed as F and the second term is expressed as P, where this F stands for effort delay and this P stands for parasitic delay. And this effort delay that is represented as F can in turn be represented as a product of G into H, where this term G represents the logical effort of a particular gate, and this H represents the electrical effort of a particular gate. And when we are trying to find the formula for this logical effort G is represented as a fraction of input capacitance of the driving gate by input capacitance of the unit size inverter. So it is a fraction of input capacitance of the driving gate divided by input capacitance of unit size inverter. So we can see an example for computing this logical effort. Then we can move on with electrical effort followed by a parasitic delay. So let us take an example for computing this logical effort. You considered a two input NAND gate. When you consider a two input NAND gate, if I want to express this two input NAND gate in terms of CMOS circuit, if you recall the concepts of the previous class, it requires nearly 4 different types of transistor, 2 for PMOS and 2 for NMOS. Now when you construct this circuit, if you recall the concept, how the NMOS will be connected is, since it is a NAND gate, the two different transistors of the NMOS will be connected in series and two different PMOS will be connected in a parallel network. And since it is a CMOS, we need to take the integration of the PMOS network along with this NMOS network, where this PMOS will be internally connected to this VDD and NMOS will be connected to this ground terminal. And let me consider the two inputs for this as A and B. Now, if you examine the aspect ratio for this particular gate, how we can compute the aspect ratio is, if the two transistors are connected in series, you just multiply the aspect ratio of the CMOS inverter with the number of input. So you know that the CMOS inverter has a PMOS as well as an NMOS network, where the aspect ratio of the PMOS will be 2 and the aspect ratio of the NMOS will be 1. The reason why it was considered as 2 is because the PMOS exhibits a low mobility when compared with the NMOS. So the aspect ratio of the PMOS will be double with respect to NMOS. Now, if you want to compute the aspect ratio of this two input NAND gate, so in this case, since the pull down network, that is the NMOS is connected in series, the aspect ratio for this network will be equal to 2. That is, the aspect ratio is multiplied with the number of inputs that are present in the circuit. So in this two input NAND gate, the number of inputs is taken as 2 and the aspect ratio of NMOS is 1. So when you take a product between these two different terms, it results in 2. And if you consider a pull-up network, that is a PMOS, the transistors are connected in a parallel fashion, and since they are connected in the parallel fashion, there is no need of multiplying the number of inputs with the aspect ratio. Due to this parameter, you can simply take the aspect ratio as such. And in the point between the drain terminal, you are going to observe the output of the gate. So when you mark the terminals of this particular PMOS, the gate source and the drain terminal will be located like this, and for NMOS, the source will be presented at the bottom, that is in turn connected with the ground terminal. Now our objective is to compute the logical effort. So if you compute the logical effort, what is the formula for this logical effort is, it is input capacitance of the driving gate, so of the driving gate divided by the input capacitance of the unit size inverter, right? So of unit size inverter. And while you are computing this input capacitance, you have to remember that this input capacitance should be included both for the PMOS network as well as for the NMOS network of the driving gate, right? It should be included for both the cases. And similarly for the inverter also, you need to compute the input capacitance of PMOS as well as NMOS, right, for the inverter circuit. So now when you are using this concept, you refer what is the input capacitance of the PMOS as well as an NMOS. So where we used to take the input capacitance will be considered at the gate terminal. So you can consider an input capacitance either at the input A or at the input B. So the top portion represents the input capacitance of PMOS and the bottom portion represents the input capacitance of the NMOS. So in this case, if you recall the concept of an RC delay model, the capacitance value is represented in the order of K, that is multiplied with the capacitance value, where this K represents the aspect ratio. So in this case, when you consider the PMOS network, the aspect ratio of this particular PMOS transistor while considering the input A is equal to 2. So this is what the aspect ratio is. Now when you take this aspect ratio for a PMOS, it is 2 and you need to multiply it with the capacitor C. And when you consider for the NMOS, here also the aspect ratio for any input, you can consider A or B. If I am considering A as an input, the aspect ratio for this NMOS is equal to 2. When you write it in a similar fashion, it represents 2C. Similarly, when you consider for an inverter, here the aspect ratio for PMOS is 2C and for NMOS it is equal to C. Now when you compute what is the logical effort of this particular case, so the logical effort can be written as G is equal to input capacitance of PMOS. So when you refer the input capacitance of the PMOS of the driving gate, the input capacitance is 2C. And similarly, the input capacitance of NMOS is also equal to 2C. So the numerator term will be 2C for PMOS plus 2C for NMOS. And when you divide it with it, it will be an input capacitance of PMOS and NMOS of an inverter. And when you refer this circuit, here the input capacitance for PMOS is 2C and for NMOS it is equal to C. Now when you substitute it, it will be 2C plus C. Now when you simplify this, it results in 4C by 3C. When both the capacitor values are getting cancelled, the resultant logical effort will be obtained as G is equal to 4 by 3. This will be the logical effort of a 2-input NAND gate. We will also discuss with one more example. We will compute a logical effect for one more gate. We can consider that you considered some 3-input NOR gate. You consider a case of 3-input NOR gate. If this is a scenario for constructing a 3-input NOR gate, if you recall how the arrangement needs to be placed is, in the case of a NOR gate, the PMOS will be connected in series and NMOS will be connected in a parallel fashion. So if you connect a PMOS network, here the number of input is taken as equal to 3. Since it is taken as equal to 3, let me take 3 different type of PMOS transistors and I will let me connect it in a series manner. And I will connect the top of the PMOS to the power supply voltage VDD and let me consider the inputs that is going to be applied to the gate as A, B and C. Similarly, if you consider the case of an NMOS, the 3 transistors of the NMOS needs to be connected in a parallel manner. So let me connect all the 3 transistors of the NMOS in a parallel manner and I will integrate it with the PMOS and let me take the output as Y. So this is how you need to create a schematic of a 3-input NOR gate. So what is the first step you need to do is, you need to compute what is the aspect ratio. So how to compute the aspect ratio is, you need to consider the CMOS inverter where in the case of a CMOS inverter, the aspect ratio of PMOS is equal to 2 and the aspect ratio of NMOS is equal to 1. And by using this concept, and one more thing what you have to remember, if the transistors are connected in series, you just multiply the number of inputs that is applied to the transistor with the aspect ratio. So when I do this kind of scenario, in this case, I am having 3 number of input. When these 3 number of input is multiplied with an aspect ratio, it results in, so here you are having 3 number of input and the aspect ratio for the PMOS is equal to 2, that results in 6. So the aspect ratio for the PMOS will be equal to 6. Whereas if I consider for the NMOS, the NMOS are being connected in parallel, so there is no need of multiplying the number of input with aspect ratio. You can simply consider the aspect ratio of the CMOS inverter that was taken into account. So the aspect ratio for the CMOS inverter of NMOS is equal to 1. So I am considering it as such as 1. Now our objective is, we need to compute what is the logical effort for this particular gate. So when I compute the logical effort, what will be the formula that can be taken is, G will be equal to input capacitance of the driving gate by the input capacitance of the unit size inverter. So when I consider the input capacitance, I can consider for any of the input. So in the previous case, we consider the input as A. So let me take a different scenario. We will take the input as B. If I consider the input as B, how the capacitance should be represented is, it should be represented in the order of K into C. So this portion will be equal to 6C and this portion will be simply equal to C. Now if I compute what is the logical effort of this particular gate, it can be written as 6C plus C, right? So divided by the input capacitance of the unit size inverter. So for PMOS, the input capacitance is 2C and for NMOS, it is equal to C. Now if I add these two cases, the numerator term will result in 7C and the denominator term will result in 3C. When these capacitance values are getting cancelled, the resultant logical effort that will be obtained for a 3 input NOR gate will be equal to G is equal to 7 by 3. This is how you need to compute the logical effort for the various NAND and NOR gates that are being asked in the question. Now, if I want to make a general expression, how to construct a general expression? So, if I want to make a general expression, so the general expression for a NAND gate. So, let me write a general expression for an n input NAND gate, right? For an n input NAND gate can be written as G is equal to, if I am considering the general case, let me write it as G is equal to n plus 2 divided by 3. Now we will cross check whether it satisfies or not. So in this example, what we considered is we took a 2 input NAND gate for our discussion. So if I substitute in this general expression, the number of input n is equal to 2. Now if I substitute in this point, it will be 2 plus 2 that results in 4 by 3. So the general expression matches with the obtained value. Similarly, you can substitute the logical effort for any number of inputs that are being applied as an input to the NAND gate. So the general expression G will be expressed as n plus 2 by 3 for a NAND gate, n input NAND gate. Similarly, if I want to write what is the general expression for a NOR gate is, so in this scenario, the general expression for a NOR gate, so for a NOR gate can be written as G, that is equal to 2n plus 1 divided by 3. So we will just cross check whether we have obtained this value or not. So if I write like this, let me take that I am going to take a 3 input NOR gate. So if I am considering a 3 input NOR gate, what will be the value of G is equal to 2 into 3 plus 1 divided by 3. That results in 7 by 3. You can see that both the values that are being obtained by substituting the general expression and by considering the aspect ratio of the transistor remains the same. So when you are computing any kind of a logical effort with respect to NAND or a NOR gate, you have to remember these kind of general expression. So let me consolidate the logical effort. So when you consider the case of a logical effort, what we are trying to do is we are trying to compute the logical effort G for various different inputs of NAND as well as a NOR gate. When you are doing a substitution like this, what you need to do is you need to consider whether the given question is NAND or not. If the given question is NAND, make sure that you remember this formula for verification purpose alone. And similarly, if you are considering it for a NOR gate, you have to consider the expression as 2n plus 1 by 3, right? So this will be for an AND and this will be for a NOR. This is how you need to compute a logical effort of a gate that is being asked. Now let me move on with the next topic that is named as electrical effort. If you consider the case of an electrical effort of a particular gate, this electrical effort is denoted as H, right? So it is denoted as H, where the formula for electrical effort will be output capacitance of the gate divided by input capacitance of the gate that is being processed, right? So when you compute the electrical effort, let me take one scenario for computing this electrical effort. So once again, for my discussion, let me consider a two input NAND gate for computing this electrical effort. So for computing this two input NAND gate, once again, let me draw the circuit for it. So for a two input NAND gate, you need to take two different types of PMOS network in parallel that is connected with external voltage VDD that is in turn connected with two NMOS transistors that are being taken in series. So for computing the electrical effort, once again let me consider my input that is going to be processed as A and B, and let me consider my output signal as Y. If this is a scenario, now when I compute this, what should I remember is I need to compute the aspect ratio once again. So if you recall the concept, the aspect ratio for the PMOS will be taken as 2 and for NMOS it is also taken as 2. Now, when you compute the input capacitance, so how you will be computing the input capacitance is, so input capacitance will be considered from the gate, right? So input capacitance, you compute it both for PMOS as well as for NMOS. Now, if this is a scenario, in this case, you can see that if I take the input as A, for PMOS, it is the capacitance value is 2C, and for NMOS, the capacitance value is 2C. So, when I compute the input capacitance, it is equal to capacitance of the PMOS that is getting added with the capacitance of NMOS that results in 4C, right? This will be the computation for input capacitance, and that input capacitance Cin will be equal to 4C. If I need the capacitor value alone, capacitor value can be simply expressed as 1 by 4, right? So this is how you need to do the computation. Similarly, if I want to compute the output capacitance, now you consider that this output is in turn connected with the capacitance in turn connected with an inverter circuit. If you consider it as an inverter circuit, how you can write the value of Cout is Cout will be simply equal to 1. The reason is we are considering the output capacitance. So this you consider that this NAND gate, if it is, you assume that this NAND gate is in turn be connected with an inverter. If it is in turn be connected with an inverter, the inverter has an input capacitance of the C that will be exactly equal to the output capacitance of the two input NAND gate. So Cout value can be simply written as equal to C. Now if I substitute the electrical effort H, H will be equal to Cout divided by Cn. So this value is Cout is 1 and Cn is 1 by 4. So H can be simply taken as equal to 4. Right? So the electrical effort that will be obtained will be equal to 4 for a 2 input NAND gate. Similarly, if I want to compute what will be the electrical effort for some 2 input NOR gate. if this is a scenario, if I construct for a 2-input NOR gate, the two PMOS transistors A and B needs to be connected in series manner, right? This is in turn connected with plus VDD, and this in turn will be connected with two different NMOS transistors that are taken in a parallel manner. So when I compute the input capacitance of this particular gate, if you recall the concept of the aspect ratio, the PMOS transistors are connected in series. You just multiply the aspect ratio of the PMOS with the number of input that results in 4. Similarly, when you consider the aspect ratio of the the NMOS are connected in parallel, so the aspect ratio will be equal to the 1, the aspect ratio of NMOS. Now, if you consider for any gate, that is for any input, let me take it for A. So, if I want to compute, this is the input capacitance. So, input capacitance will be equal to the input capacitance of the PMOS, that is 4C, plus the input capacitance of NMOS, that is equal to 5C. So this capacitance Cn can be written as equal to 1 by 5. Right? Similarly, if I want to compute output capacitance, you consider that this NOR gate is in turn connected with CMOS inverter. If this is a scenario, the output capacitance will be equal to 1. And if I substitute these values in H will be output capacitance by input capacitance. So H can be taken as equal to 5. So this will be the electrical effort for NAND as well as NOR gate. If I try to write the general expression for electrical effort as we did in the previous case, how we can write the general expression is, so in general, the electrical effort can be expressed as, suppose if I am considering a NAND gate, it needs to be written as n plus 2, where n represents the number of inputs, right? Similarly, if I want to represent for a NOR gate, it can be represented as simply as 2n plus 1. This n represents the number of inputs. We will also cross check whether this value is obtained or not. You consider that you are going to compute an electrical effort for a 2-input NAND gate. If I want to compute the electrical effort for 2-input AND gate, so the number of input is 2, that is added with 2, that results in 4. Similarly, if I want to compute the electrical effort for a 2-input NOR gate, in this case also you can see that it is 2 into 2 plus 1, that results in 5, right? So when I cross check with these values that are obtained initially, it is getting matched with these values. So the general expression for computing any kind of electrical effort for NAND as well as NOR is going to be this kind of scenario, right? This is how it needs to be computed. Similarly, if I want to compute the last term, that is parasitic delay, so how to compute this parasitic delay is, so if I consider an parasitic delay of an inverter, it will be simply written as equal to 1. And similarly, if I am taking an NAND gate, so the parasitic for this NAND gate will be written as n into the parasitic delay of P inverter. So if I need to compute what is this parasitic delay, so how we can define the parasitic delay of any kind of CMOS network is, so it can be defined as the parasitic capacitance element. How this going to be happen is this parasitic capacitance depends on the gate capacitance, source or drain that is being set as a diffusion capacitance and an interconnect capacitance. So in general, the parasitic capacitance can be computed by taking a multiplication of R and C. That is what we will be doing in the case of parasitic capacitance. So now if I compute this kind of parasitic capacitance and for parasitic delay for any kind of two input NAND gate, if I want to consider it for a two input NAND gate, so once again let me draw the schematic for the two input NAND gate for your understanding. Let me take the two inputs like A and B and output as Y. Now, when you compute this parasitic delay for this NAND gate, if it is a two input NAND gate, the formula that is given is you take the number of inputs that is multiply it with the 2. So, the parasitic delay for a NAND gate will be simply equal to 2. And how this parasitic value of this particular inverter is equal to 1 is, so when you are writing in this case, so you can see that this value is 2C and this value is C. When you compute the parasitic delay, what is the formula is the input capacitance of the driving gate divided by input capacitance of the unit size inverter, right? So it will be 2C plus C that results in 3C by 3C. So the parasitic value will be equal to 1. In general, how we can define this parasitic delay or how to compute the parasitic delay is you just consider the number of inputs that are being applied to the gate. When you consider the number of inputs that are applied to the gate, you can see that in the case of a 2 input NAND gate, the parasitic delay value is equal to 2. And in the case of an inverter, we are applying only one input, so the parasitic delay value is equal to 1. Now, if I want to compute a normalized delay using a linear delay model, what will be the formula for the normalized delay is D will be equal to F plus P. And you know that this D can in turn be written as G into H plus P, right? So if I consider some gates, so you take that I am going to compute this normalized delay for a two input some NAND gate. So if this is a scenario, D will be equal to G. So what is the logical effort? If I go back to the previous topics, we computed the logical effort of a two input NAND gate as G is equal to 4 by 3. And what is the electrical effort that we computed for a two input NAND gate is the electrical effort was obtained as 4. So if I take this kind of values and if I substitute in this equation, so for a two input NAND gate, the logical effort was obtained as 4 by 3 and for the electrical effort it is obtained as 4 and the parasitic delay is obtained as equal to 2. Now, when I compute this delay, it will be some 16 by 3 plus 2 and if you take an LCM, the denominator is 3. So, it results in 16 plus 6 that results in 22 by 3. So when I compute the delay, normalized delay using a linear model for a two input NAND gate, the resultant linear delay model produces a delay of D is equal to some 22 by 3. So this is how you need to compute the linear delay model for any kind of gate that is being asked in the question. So you have to just remember this one formula alone, that is D is equal to F plus P, that results in D is equal to G into H plus P. So this formula needs to be remembered while you are computing these kind of linear delay model. So we have seen a simple example by considering some two input NAND gate, and we computed the linear delay model. Uh, in the preceding classes, we can also see few more examples that is related with this kind of linear delay model, right? So thank you all.